A ring of mass m, radius r, and rotational inertia mr squared is initially sliding on a frictionless surface at a constant velocity v0 to the right as shown. At time t equals 0, it encounters a surface with coefficient of friction mu and begins sliding and rotating. After traveling a distance L, the ring begins rolling without sliding. Express all answers to the following in terms of m, r, v0, and fundamental constants where appropriate. Starting from Newton's second law, in either translational or rotational form, as appropriate, derive a differential equation that can be used to solve for the magnitude of the following as the ring is sliding and rotating. The linear velocity v of the ring as a function of time t, the angular velocity omega of the ring as a function of time t. And derive an expression for the magnitude of the following as the ring is sliding and rotating. The linear velocity v of the ring as a function of time t, and the angular velocity omega of the ring as a function of time t. Starting with Newton's second law, net force equals mass times acceleration, and since we're making a differential equation, let's use the differential version of this. F equals m dv dt. The only unbalanced force in this problem is friction, and it's in the opposite direction of velocity. Frictional force is mu, force normal. And in this problem, because it's rotating on a horizontal surface, the normal force is simply mg. We have an m on each side of the equation, so the masses cancel. We don't need to know the mass of the ring. So this gives us the differential equation that we're looking for. We can now perform a separation of variables on our differential equation. We can take dt and move it to the other side by cross multiplying, leaving dv all by itself. Now we can integrate each side. The dv we're going to integrate from v0 to v final. And on the right side we're going to integrate from 0 to t. Integrating gives us v from v0 to final velocity, and integrating the other side, the negative mu g can be pulled out of the integral. They're constants. So I'll have negative mu g times t from 0 to our final t. So this gives us v minus v0 equals negative mu gt minus negative mu g 0, which of course just goes away. And finally, we can move the negative v0 to the other side and isolate our final velocity. And this is the expression that we're looking for. Now let's derive a differential equation that can be used to solve for the angular velocity of the ring as a function of time. We'll start with Newton's second law, but this time for rotational motion. The net torque is the moment of inertia times the angular acceleration. And let's use the differential form for angular acceleration since we'll be making a differential equation. That's d omega over dt. In the problem, we're told that the moment of inertia is mr squared. This net torque is, of course, created by the force of friction. This time we're going to use a positive value since it will create a counterclockwise rotation. The force of friction times the radius of the ring. The force of friction in this case is again mu times the normal force, which is simply mg. And we notice now that the m's cancel. Again, we don't need to know the mass of the ring. And we also notice that a radius cancels from each side of this equation. We can now divide the radius to the other side, and this gives us the differential equation that we're looking for. d omega dt equals mu g divided by the radius. We can now use this differential equation to derive an expression for the magnitude of the angular velocity of the ring as a function of time. We can perform a separation of variables on it, cross-multiply the r to the left side, and cross-multiply the dt to the right side. We can now integrate each side. Integrating gives us r omega equals mu gt. And doing a little cross multiplication, we come up with the expression we're looking for. Angular velocity equals mu gt divided by the radius. Part C asks us to derive an expression for the time it takes the ring to travel the distance L. Starting with the expressions that we've already derived for velocity and angular velocity, and the relationship between velocity and angular velocity, because that's the point at which it will be completely rolling and not slipping, is when the velocity equals r times the angular velocity. And now we can just substitute into this expression for v and for omega. We can see that the radii cancel out. We don't need to know the radius of the ring to solve this problem. And now let's take all the expressions that have t in it and move them together to the same side. We can now factor out a t. And inside the parentheses we're left with 2 mu g. We can divide out the 2 mu g to isolate t. And let's just clean this up a little bit and put t first. And this is the expression that we're looking for. T equals v naught divided by 2 mu g. Part D of this problem asks us to derive an expression for the magnitude of the velocity of the ring immediately after it has traveled the distance L. So we can take the expression that we derived for the velocity and the expression that we derived for the time and simply substitute the time into the velocity equation. This gives us v equals v naught minus mu g times v naught over 2 mu g. Notice that the mu g's cancel out. V naught minus a half of v naught is simply a half of v naught divided by 2, and this is the expression that we're looking for. Part E asks us to derive an expression for the distance L. Displacement is the area underneath the velocity versus time graph. So therefore, the distance L, which is the magnitude of the displacement, is going to be equal to the integral of our velocity function with respect to time. Our limits will be from 0 to the amount of time it takes to stop slipping. Now we've already derived a formula for our velocity, so we can simply substitute this into our integral. We've also derived an expression for the amount of time it will take. we can substitute this into our limits of integration. Evaluating this expression, we get v naught t minus mu gt squared divided by 2 from our limits of 0 to the upper limit. Evaluating this expression, we plug the limits in. We can combine our v naughts into v naught squared. We can also square everything inside the parentheses and get rid of the square that's on the outside of the parentheses. And finally, the 2 and the 4 can multiply together to give us 8. And now we can get a common denominator for our two terms by multiplying the numerator and the denominator of the left term by 4. And by canceling out a mu and g from the left side. Four v naught squared minus v naught squared is equal to 3 v naught squared. And this gives us the expression that we're looking for.